In Concept B, we're just going to be focusing on ionic bonding and also spending some time looking at how to draw Lewis dot structures representing ionic compounds. So we're going to talk a little bit about properties and various examples of ionic compounds. We'll mention a little bit about electronegativity difference and how to use that to identify an ionic bond. We're going to be drawing, again, like I said before, Lewis dot structures to represent these ionic compounds. So first, let's just go through a couple of properties. One thing I want you to keep in mind is that we've talked previously in Unit 5 about properties of metals and nonmetals, and when we studied the periodic table. So you kind of have to step away from those properties because we're going to be talking about different properties that these elements take on once they form an ionic compound. So ionic compounds have high melting and boiling points. They tend to be hard and brittle means that we could crush them into a powder, which is very different than our pure metals that we talked about. And in terms of their conductivity, ionic compounds are a little strange because they're sometimes conductive and sometimes not. Two things we have to think about when figuring out their conductivity is, are charges present, and then are those charges able to move? And for ionic compounds, they can only conduct electricity when they're in a liquid or solution phase. Or liquid phase or as an aqueous solution. Ionic compounds can conduct electricity because the charged ions, those positive and negative charges, are free to move. However, as a solid, we're going to see in the next slide that ionic compounds are in a crystal lattice, which means they're basically stuck in place. So even though we have charges present as a solid, it's not able to move. So again, conductivity in ionic compounds, you want to think about if it's in a phase such as a liquid or a solution compared to as a solid. So that's a common multiple choice question that you could see. Here's kind of a graphical representation of that. Here the positive on the left, the positive negative ions are fixed in a solid. So because while we have charges, they're not able to move, we can't conduct a current. However, once those charges are able to move as an aqueous solution, it will conduct a current. Alright, so we just mentioned something called a crystal lattice. Well, that's how ionic compounds exist. They don't exist as single molecules, but in this crystal lattice. So the positive and negative ions arrange themselves in a pattern, and there's various patterns that they can arrange themselves into. And these ionic bonds, they can be disrupted or broken by melting or dissolving in water. So I can actually break these up. This is usually how it's arranged as a solid crystal. So one thing you want to keep in mind is we talked about before that ionic bonds occur between a metal and a nonmetal. And we've also talked about the influence of polyatomic ions. But here we're just going to focus on metals and nonmetals. And because of the metal and nonmetals difference in electronegativity, there's a complete transfer of valence electrons. So in this example, we have a sodium atom and a chlorine atom. The sodium, which has 1 valence electron, and the chlorine that has 7, the sodium is going to give that valence electron away to chlorine, so that they become a +1 sodium ion and a -1 chlorine ion, which then attract each other and then arrange themselves with other ions to form that crystal lattice. So I talked about the electronegativity difference between the metal and the nonmetal, and because of their electronegativities, they're going to be greater than 1.7 if we subtract them. So the atom with the higher electronegativity, which is usually our nonmetal, is able to pull and remove the electrons from the atom with the lower electronegativity, which is that metal. So just a quick example, this isn't in your note packet. There's an example between that I gave you of sodium and chlorine. EM being the electronegativity of Na in chlorine. You would have to go look in your reference table right behind the periodic table and look up chlorine and sodium. And you'll see that sodium has a 0.9 and chlorine has a 3.2. When I subtract them, I get a difference of 2.3. Since that is above 1.7, this indicates that an ionic bond formed between them. So just one thing to keep in mind as we're getting deeper into this unit of being able to calculate that to help you identify different types of bonds, specifically here ionic bonds. So our metal atom, which loses its valence electrons, is going to give them to the nonmetal atom, which gains them. So the number of electrons lost or gained will be the number needed by each atom to form a stable octet, so that 8 valence electrons that we referred to yesterday in class. So when we're talking about drawing these, we want to keep that in mind, that the metal atom is actually going to lose all of its valence electrons, and the nonmetal is going to gain all of those to get a complete shell. So in ionic bonding, the metal atom, because it's going to be losing electrons because the positive becomes the positively charged ion, and the nonmetal atom that gains those electrons is going to become the negatively charged ion. Remember, these movement of electrons, you want to be thinking about the ratio of protons to electrons and how that influences the positive or negatively charged ion. So we'll come back to this in class if you don't recall this from our atomic theory unit. So again, sodium's completely transferring its valence electrons to chlorine, which then fills, and you can see those charges of positive and negative. All right, so just keep in mind, remember, they're losing and gaining electrons in order to achieve the electron configuration of a stable noble gas. So our metal or positive ions, how do we draw this in our ionic compound? So we're going to be looking at drawing our Lewis dot structure for our ionic compound. So all the valence electrons are lost, so it has to have 0 electrons in its valence shell. So to draw the metal, we're going to write a symbol. We're not going to put any dots around it. And then we're going to write the charge in the upper right-hand side. And we went over placing brackets around the symbol and putting the charge on the outside of it. So for calcium, which normally has 2 valence electrons, it's going to lose both valence electrons. And then we put the charge of +2. And again, you can have brackets around the Ca part in between the Ca and the +2. If I have rubidium, which has 1 valence electrons, it becomes a +1. And then aluminum becomes a +3. So again, our positive ion will always have 0 dots drawn around them. Now our nonmetal is going to gain enough valence electrons to be full. So it's going to have 8 electrons in the valence shell. So we're going to write a symbol. We're always going to put around the nonmetal 8 dots. We're going to place brackets around it and then put the charge on the outside of the brackets in the upper right-hand side, depending on how many electrons it gained. So for example, chlorine, to get its full octet, needs to gain 1 valence electron. So we're going to add that in to give it 8, and then put that 1 extra electron as a -1 charge. Sulfur needs 2 valence electrons. It already has 6. So we're going to put the -2 on the outside, making sure that we show a full octet or a full 8 electrons. And then finally, we have for our last example, nitrogen, where it needs 3 valence electrons in order to go from 5 to 8. So again, 8 dots with a -3 charge. So let's put this all together, putting our metal and nonmetal ions to form our ionic compound. So to draw the dot diagram of the ionic compound, we're just going to put the ion dot diagrams next to each other. Now the ion charges cancel. They should always add up to 0. So if I add up all the charges of each ion, they should add up to 0 in the compound. The opposite charged ions are attracted to each other, and the like charged ions have to be as far away from each other as possible. So we should never have 2 negatively charged particles, ions, or 2 positively charged ions together. So let's look at 2 examples. Lithium fluoride is our first one. We would look at their dot structures, lithium having 1 valence electron, fluorine having 7. We're going to see that that 1 electron will be given to fluorine. So lithium becomes a +1 and fluorine becomes a -1, and then this would be our final ionic compound structure. So again, showing that these add up to 0. The positive ion has 0 dots, the negative ion has 8 dots, and that's complete. Now here we have beryllium fluoride. Oh, and sorry, we can see that on the bottom here they add up to 0. Here I have 1 beryllium, 2 fluorines, and you should be able to see that each fluorine is going to get 1 of the valence electrons from beryllium. So when we actually draw these out, we want to make sure that the fluorines are as far away from each other as possible. So we're actually going to place them on the outsides of beryllium. Beryllium gave up 2 valence electrons to become +2. Each fluorine gained 1. And then we can check the charges, and they add up to 0. Alright, so those are some examples. We've learned already how to draw ions. So it's really just about putting it together to make an ionic compound. So that is it. So make sure, check over your notes, make sure it's all set, and we will be working on these ionic compounds and talking and discussing more about ionic bonds in class tomorrow.